I would like to compare some different terms which all sound similar and can therefore confuse students. Atomic number is number of protons. Remember, atomic number is linked to elemental type. For example, nitrogen always has 7 for its atomic number. Atomic number is written on the bottom left of an atomic symbol. Mass number is protons plus neutrons. Since isotopes of a particular element have different numbers of neutrons compared to each other, they have different mass numbers. We call it mass number, but it's not exactly how much an atom weighs. Instead, it is counting subatomic particles in the nucleus of a particular atom. Mass number is written in the top left of an atomic symbol. Average atomic mass is something we haven't mentioned yet. It's confusing because it has the word atomic in it and the word mass in it, but it's totally different from atomic number or mass number. Average atomic mass is how much an atom weighs. It is not, however, the kind of average you are used to where you add all the numbers, then divide by the number of numbers. Instead, it is a weighted average, and is based on how abundant each of the isotopes is. The average atomic mass can be found at the bottom of each square on the periodic table, and will be a decimal value rather than a whole number. We can calculate average atomic mass by finding the sum of the fractional abundances times their isotopic masses. Let's look at boron, for example. It has two main isotopes, boron 10 and boron 11. Boron 10 has a mass of 10.0129 AMU and an abundance of 19.9%. Boron 11 has a mass of 11.0093 AMU and an abundance of 80.1%. Notice that the abundances add up to 100%. This should always be the case. I could have given you just one of the two abundances, and then you could subtract from 100 to find the other one. Our first step would be to take those abundances in percentage form and turn them into decimal form by moving the decimal point over 2 places to the left. We would write 19.9% as 0.199, and we would write 80.1% as 0.801. Those fractional abundances will tell us how much weight to place on each of our masses in our weighted average. The one that's more abundant will count for more in our average, and the one that is less abundant will count for less. We take the abundance of boron 10 in decimal form and multiply it by the mass of boron 10. Then we take the abundance of boron 11 in decimal form and multiply by the mass of boron 11. And then we add the results to get the average atomic mass of boron. We come out with 10.811, which is the number listed in the square for boron on the periodic table. If there were more isotopes, we would include them in our calculation. For each isotope, we would do its fractional abundance times its mass, and then we would add up all of the results at the end. I recommend doing the whole calculation at once in your calculator, using parentheses, so you can avoid rounding error. Always use the full value of the masses given in your calculation. Do not round them. If you end up needing to round at the end, keep the same number of digits as the original masses. The abundances of each isotope can be determined with mass spectrometry. Each isotope would have its own peak in the mass spectrum, due to having different masses. The area under the curve for each peak could be measured, and the relative amounts could be used to find the percent abundances. The natural abundance of copper-63, weighing 62.929599 AMU, is 69.17%, and the natural abundance of copper-65, weighing 64.927793 AMU, is 30.83%. What is the average atomic mass? Is it A, 63.54 AMU, B, 62.93 AMU, C, 64.93 AMU, or D, 127.86 AMU? To calculate the average atomic mass, we're going to take the mass of the first isotope, which is 62.929599, and multiply it by its abundance in decimal form. So we changed the 69.17% into a decimal form as 0.6917. We're moving the decimal point over 2 spots. Then we're going to do the same thing for the other isotope and add them together. So the other isotope has a mass of 64.927793, and we multiply it by its abundance in decimal form, which is going to be 0.3083. Again, we've moved the decimal point over 2 spots. And I like to do this all in my calculator. Just make sure you put in the parentheses so that it does it correctly. So when I do that, I come out with 63.54314 AMU, and we can round that to get A, 63.54. Notice this is a weighted average, not your traditional average. We're not taking our two masses of 62.929599 and 64.927793, adding them up and dividing by 2. Do not do that. That would essentially be weighting them each 50%. But we need to weight them according to their abundances so that we can get the correct weighted average atomic mass.